Good evening to all. My name is Vishnu and it is my pleasure to welcome all of you for our fourth webinar as a part of #Q Thursday. The topic of this week's webinar is quantum computing for finance. You will get a brief overview of quantum computing and how it differs from classical computing. You will learn about the different ways to use algorithms in order to make quantum computing more useful, as well as the various ways in which algorithms can be applied to financial problems. Finally, you will learn about quantum algorithms for derivative pricing by an example. Before we start, I request everybody to join us for 1 minute of silent prayer. Thank you. It is my pleasure to introduce today's speaker, Dr. Rajiv Krishnakumar. He is the Executive Director of R&D Engineering Team, Goldman Sachs, Switzerland. Dr. Krishnakumar received his PhD in Experimental Applied Physics at Stanford University in 2017. After his graduation, he took up a joint postdoctoral fellowship position at AT&T Foundry and Caltech, working on quantum speedups and machine learning algorithms. He then joined the Securities Division at Goldman Sachs as a data scientist, and afterwards, he moved on to the R&D team where, for the past 2 years, he has been working as a research scientist in the fields of quantum computing. His current primary goal is on applying quantum algorithms to the field of option pricing and machine learning, as well as understanding if a quantum advantage can be attained in these fields. A hearty welcome to you, sir.
Thank you very much.
Before we start, I request the audience to kindly keep themselves muted. If you have any questions, you may post them in the chat. All doubts will be clarified in the Q&A session towards the end. Now, I invite Dr. Krishnakumar to take over. Sir, please.
Thank you. Thank you very much for that very kind and very clear introduction. And actually, one of the questions that I was asked before the session was if I could talk a little bit about my journey, but I think you've done that very, very well. So I appreciate that. Thank you to Dr. Lincy as well for inviting me today, and to IIT Kottayam. And I'm very, very happy to be here today. Actually, in the poster in the top right corner, there is also a QIndia logo. So just to be clear, IIT Kottayam and Professor Lincy are the main organizers, and QIndia was a little, let's say, sponsor maybe. And I thought I'd spend 1 second on QIndia and talk about what we do. So at QIndia, we are a community of people that are centered around quantum technologies with a focus on India. So hopefully you can see, just to be sure that the thing is clear, the presentation is just that of okay, great, thank you for the thumbs up. So it's a community centered around quantum technologies with a focus in India, where we spread knowledge, make the field accessible to all diverse groups, create ways for people to collaborate, etc. So this is just some shameless advertising. This is a community where everything is free, and everyone that participates in it is a volunteer. So it's really out there for people to join if they would like. We live mainly on Discord, and if people would like more information about how to be part of this community, always happy to answer those down the line or post a link in the chat. Okay, so with that being said, let's get started with the presentation. So let's see, let's see if I can present this. Okay, if I share this, does everybody see the screen? Let me see. Nope. Okay. Should have tried this before. Let's try one more time. Here we go. It's blinking, is it? That's not very good news. It's blinking. Let's try one more time, and if it blinks, then we'll have to take a 30-second pause as I send my presentation to a different screen. Let's try one more time. It looks like it's going to blink again. Okay. Yeah, I'm really sorry for this. Usually I'm not on Google Meets, so this is a little bit new for me, but if you will give me just 30 seconds.
No problem. Take your time, Lincy.
I apologize.
No problem. Hi, Rishi. You can post the QIndia invitation, membership, Discord server, everything on the chat, maybe.
Can you hear me? I'm not sure if this is working.
You're not audible.
Okay. Yeah.
Yeah, I think I had a low volume. Yeah.
Can you hear me?
Yeah.
Can you hear me?
Yeah. Yes.
Okay. Right. I think good. Yeah. I will post the registration form here. Thanks. Good to see you.
Because that was very important, like I started learning everything through when you conducted Q Bronze. So that was the starting. So I should tell that because it will be helpful for others also. Like you can also start your journey with Q Bronze, Q Silver. They have many certifications related like this. And I think recently Q World had a Q course, right?
Yeah, exactly. Mm-hmm.
Yeah. And if you are really into quantum computing, you can also look into the projects people are doing related, like connected with QIndia and Q World.
Exactly. So I think one of the best things is it's a global network, and then it's not, you have a lot of resources from all over, right? So this Q Bronze and Q Silver, so Q Bronze especially, it assumes no prerequisite. Like if you know basic matrices that you learn in your 12th and then some basic Python, then it's that's all it assumes, right? So then it's a very good, I think if you sit with it, it's a good introduction. And there are a lot of these so Q intern opportunities are also there, so you get to collaborate with people from all over. I think it's a good venture.
Yeah.
Happy to, and so I see. So that my stuck or
yeah, some network.
Okay, I see. It was me. Sorry. Yeah, no, I was asking if this was the final Q Thursday session, or if you're going to have more.
No, actually, next week also we have a Q Thursday.
Nice.
So with next week we are closing, and it will be really good if you could come actually. And a person from UST Global so they are doing some research in quantum. So
right. So
I thought
the next Q bronze, we're trying to have it in April.
Oh, that's
we're not
great.
super sure. So,
Okay.
but if you're part of the Discord server, so once you fill in this Google form, it's a bit long, but then we get to know the audience, and then we get to help them a bit better, hopefully. So once you do that, towards the very end, when you hit submit, you get a message, and over there is this Discord link, which where, like Rajiv said, is where we live basically, and all these announcements will be posted there. So, and if you're having any difficulties with everything, just I see that Rajiv joined, so I'll just QIndia. I'll just put the email here, and then you can write to us there. Perfect.
Great.
Yeah, okay.
Thank you, Rishi. And thank you, everybody, for your patience. So now let's try it one more time, and hopefully this should be looking pretty decent.
Yep.
Yeah.
Okay.
Good.
But it's not on full screen mode.
Yes. Okay. Great. So let me put it on full screen mode, and let's get going. Okay. Oh. So if I do this, does it go into full screen mode? Now there we go. Nope. Still not happy.
No.
All right, we'll get there eventually. Stop presenting. Let's go and start presenting. Window. Okay. All right, we made it. Okay, thank you everybody again for that patience, so we can get the show on the road. So today I'm going to talk to you about quantum computing applications for finance, but as Vishnu pointed out, a lot of it is going to be more of an introductory material into quantum computing, so that when I talk about potential financial applications, it all makes sense. So I will be pausing periodically for questions. So as was mentioned by Vishnu, please feel free to write questions in the chat, and I'll periodically pause to look for them. And I'll also we'll also have plenty of time at the end for questions. There were also some questions that were sent to me beforehand, which I will try and answer along the talk. Okay, great. So this presentation has kind of two slides, which I think if you don't take away anything from it, maybe is what you should take away. And this is the first slide. And it says, the important questions that we ask ourselves is, how powerful a quantum computer do we need to be able to get quantum advantage in finance? And the very non-complete first sort of estimate answer is that first estimates for use cases of derivatives pricing and risk analysis, we need a roughly 10,000 logical qubit computer that can run over 1 million operations in a matter of seconds. So the next slide, that will be the main takeaway, will be given to you closer to the end. So that would be the second takeaway slide. And that'll just basically restate this, but in a more, with a bit more details. And hopefully the presentation, by the time we get to that second slide, will make you understand what those details are. So don't worry if this doesn't, you don't understand all of these sentences yet. So hopefully by the end, you'll have some idea of what these things mean. Okay, so before talking about quantum computing, let me talk about quantum computing at Goldman Sachs. So at Goldman Sachs, we're a bank, and we have a quantum computing team. And the goal of our team is to bring quantum advantage to finance. So what does that mean? Well, at the bank, we use computers to calculate many things. And what we want is to see if we can use quantum computers to compute calculations of interest more efficiently and or faster than current methods. Really, that's like a lot of the goal of many quantum teams is to get to this, especially end user teams. And we also not only want to find where we can calculate things faster, more efficiently, but it has to be much faster. So it has to be very significant. And it also has to be in an area that is quite large in our business. So even if we find a way to calculate something that we care about much faster, but we don't actually use it very broadly, then that's also not as interesting. Right? So that's kind of the big picture of why we're around. What does that mean that we do on a day-to-day, right? Because this is all nice, it's a big picture, but on a day-to-day, really what we do is we do research, and our main deliverables are academic papers. We have some patents and maybe some in-house projects, but really the main crux is to produce research and put it out there. And if you think that's kind of strange for a bank to be putting out research as opposed to keeping it proprietary, it's even more interesting because we not only do research, but we collaborate with other companies, institutions, and universities to do this research, right? So really, this is a bit of a different take than most teams at the bank. So the question is, why would we do this, right? At a bank which typically keeps things proprietary? Well, the answer is because right now, quantum computer is at a very, very nascent stage. And there needs to be a lot of infrastructure that needs to be built before we can even think of, okay, how can we use some algorithms to make money on a real quantum computer, right? And I think a kind of catchphrase is it's time to grow the pie before we take a slice. So we really believe that we need to work as a large community together to get to a stage where then companies, not just us, but many companies can start using it to for commercial purposes to make money. Okay, so let me pause for a second if there are any questions on that, but then I will go towards quantum computing and talk about that in general. Okay, I see no questions about this on the chat, so for now I'll keep going. Great. So okay, quantum computing. So quantum computers require hardware, software, and algorithms to be useful. I've highlighted the word algorithms because that's mainly the work that I work on. I don't work on building the hardware or creating large amounts of open source software. And so that's basically the mainly of what I'll be talking about today. And in terms of algorithms, the things you can do, they need to be discovered and they need to be implemented as efficiently as possible. Some algorithms typically are discovered in a more abstract sense, and then you need to be able to find out how to go from that abstract sense to an actual implementation on a quantum computer. So this talk will be discussing how we are looking to push research in the algorithms field with a small application, with an application to finance, but the first part will be generally what are the things that at least I think of and some of the other researchers think of. So the rest of the talk will go like this. So I will talk to you about quantum computers, where we are today with the technologies, how they actually work, and the long-term goal of the work that needs to be done in algorithms to get to a place where we can reach quantum advantage. So again, quantum advantage is a term that you hear a lot, and this is the idea that I mentioned previously, where you want to use quantum technologies, and in the case of quantum computing, to compute something faster or more efficiently than the current method. That's the general idea of quantum advantage, in a way that's sustainable. So not just in like a one-off example. Okay, and then if we have time, I do want to take a good pause before talking about the example, because the example is a little bit technical and it goes into details, and so I would like to gauge whether the audience is interested in diving into that or talking about things in general. Okay, so let's start with what is a quantum computer? Well, it's a type of computer, and as is not super surprising, it has a hardware component, a software component, and an algorithms component, and they all have to work together. And this is no different with a quantum computer than it is with a classical computer in terms of the way you can bucket things. And so first, I want to talk to you a little bit about the hardware and software, actually, and then I'll spend most of my time talking about algorithms. But in the hardware, okay, where are we with the hardware today? So let's take a snapshot of the computer hardware history. So in the 1940s, early 1940s, we had our first electronic digital programmable computer. And then in the late 40s, we had the first store programmed computer, which essentially means the first computer with some memory that could stay for a while. And quantum computers today, you can think of them as kind of early 40s stage. So we have quantum computers in the world today. We can program them, but firstly, they can't store any quantum memory. And even then, it's a bit of a push to say that we're actually at this similar stage as computers were in the early 40s, because right now, quantum computers are very, very noisy, and they are not, we don't have a immediate commercial use case today. And so to give you an example of what you can do with a quantum computer today, oh yeah, well, we can actually, before that, good point, I wanted to talk about the software, and then I'll talk to you about what we can do with a quantum computer today. But just to give a similar picture in software, first we thought of computers with logical circuits. So these are inputs, and you have these gates, these like transistors essentially, and then you output some number, and then you got it a little bit more abstracted with assembly code, and then you went to kind of C programming, C++, and Python, which is even a little bit more, you have to worry about fewer things, and so on. And then the rest is history. In quantum computing, we still think of things at a logical gate level. It's too early to abstract things away so quickly. You might notice that this is written in Python, but we use Python to create these logical circuits. So conceptually, we are still thinking about stuff in like a logical circuit way. So we have a while to go in the software as well. So given that we have this hardware and the software today, what can we do? Well, we can ask a computer, okay, we can ask a quantum computer, what are the factors of 21? A times B equals 21. What are A and B? And it can tell you 7 and 3, or well, maybe 8 and 3, but probably 7 and 3. Okay, so you're thinking, okay, great, thank you. Like if that's how useful it is, maybe we shouldn't be using it today to solve all our world's problems. But why should we care then if we've spent so much time to build a machine that can sometimes or most of the time tell us that 21 is actually 7 times 3, but sometimes it doesn't get that right? So the answer is because at a very fundamental level, quantum computers work differently to the way that computers work today. And we think that that has a potential to solve problems of large scales that we can't do today using classical computers down the line in the future. And so the next part, I'm going to be talking to you about how do quantum computers work, to kind of talk about why it is that people think this way, that we can really potentially solve very, very difficult problems that regular computers cannot solve today. So let's go back to this circuit idea to talk about the differences. So in regular computing, everything is in Boolean logic at the end of the day. So you have a bunch of ones and zeros, and you have a bunch of these gates that can take these bits as input and output other bits, depending on what calculation you're trying to do. Then you have some sort of another device that's known as probabilistic computing. This is not so prevalent in today's world, but there are sort of niche examples where instead of just a definitive bit, you have some probabilistic bit. Some bit that can be with some probability 0 and some probability 1, and you act on it with something called stochastic matrices. And so at the end, you have some bits that are in 0 or 1 with different probabilities. You measure them, and you can make calculations using this. And then conceptually, the next step is kind of these quantum computers, which no longer use bits or probabilistic bits, but they use quantum bits, or qubits, as they're known for short. And so you can see that this is an example of how we write a qubit. We say alpha 0 plus beta 1, where the probability of measuring 0 is alpha squared, and the probability of measuring 1 is beta squared. Now, you might think this looks very similar to a probabilistic bit, and it kind of does, but the little twist is that alpha and beta can be complex numbers, so they can have an imaginary component, or the I, to them. And this might seem a little bit unusual, but it means that we can do more things given this system than we can on a probabilistic bit. And exactly what those things are kind of going to be talking a little bit about the rest of my talk, but they're not obvious. In addition to, by the way, the qubit having imaginary components, sort of by definition, the operators also have imaginary components. So these gates, right? The gates in quantum computers also can have imaginary components. And for those of you who are familiar with linear algebra, they have to be unitary operators acting on the states. Okay, and then in one sentence, I will say the idea of adding an imaginary component leads to interference, I think, and that is very briefly what gives a potential advantage for quantum computers. But I can talk about interference more in detail if people would like, but I think I'll leave it at that for now so that we can continue with the rest of the presentation. So maybe I can talk a little bit about a simple quantum circuit that will generate and measure a Bell state. So this is for those of you who are a little bit more familiar with this type of stuff. If you're not, that's okay. I'll go through this example and then I'll go back to a sort of bigger picture. But the circuit on the left describes how to create a Bell state and then measure it. And I'm going to start off by saying, okay, if my two qubits are 0, 0, I'm going to write this vector. If they're 0, 1, I'm going to write it as this vector where the 1 is in the second spot, 1, 0, 1, 1. These are just definitions on the right. So in the beginning, when I'm here, I just have qubits that are in 0, 0, so I'm going to write my vector as such. And then I'm going to act on the first qubit with something called a Hadamard gate, but it's just a word to say that if my qubit is in 0, I'm going to put it in an equal 50-50 superposition. So I'm acting on this in the first qubit. And the second qubit, I do nothing, so I act on it with the identity. So if I'm acting on something with the Hadamard and the identity, I create this matrix. This is my operator. So I'm going through this very quickly. I'm not expecting people to follow line by line, but the idea is that you have some operators and they can be written as some matrix. And then this matrix, I multiply it on my state to get what comes out after the qubits go through these operations. And in this case, it's a state that's 50% in 0, 0 and 50% in 1, 0. Then I act on it with another unitary operator or another gate. And this gate says, well, okay, if my first qubit is in the 0 state, flip the second qubit. If it's not, then don't do anything. So this is, again, I write it as a matrix. I multiply it by the state that it's in, and I finally get my answer. So this is what's called a Bell state. It's a state that's highly entangled or correlated. You can see that if you measure that the first qubit is a 0, the second qubit will also be a 0. And same thing, if you measure the first qubit being a 1, the second qubit will also be a 1. Okay, and I can rewrite this whole thing as without working in matrices as well. So I have my 0, 0 qubit. I act on the first qubit with an H gate. So my first qubit becomes 0 plus 1. And then I act on for both qubits with a controlled NOT gate, it's called. And then it becomes 0, 0 plus 1, 1. And then I make a measurement and I'll either measure 0, 0 or I'll measure 1, 1. Okay, so that was just to give you a flavor of how people think about circuits and manipulating qubits in a quantum machine. I will pause if there are any questions. Again, not expecting everybody to understand everything that I just said, but really the idea was to give you a flavor of how we think about these logical circuits and quantum bits, and show an example which you cannot do on a classical computer. Not necessarily an example you would want to run for a commercial use case, but just a little toy example maybe. And that has profound physics implications, but in terms of computing a value for a commercial use case, it's just as a toy example. So I can wait for a couple of 30 seconds or so to see if anybody has any questions on that. Okay, great. I will move on now to the sort of longer term goal of what we need to do for quantum advantage. So, how do we think of quantum algorithms? And there are many ways of thinking about it, but they're kind of, in my mind, there are 4 buckets that you can think of quantum algorithms in. And they're not mutually exclusive or very separate, or maybe not even all encompassing, but in my mind, these are kind of some big aspects that I think about. So one way to look at quantum algorithms to try and push the field forward to make them useful is a top-down approach. So you look at something that you would like to compute, and you say, okay, well, that is some calculation that I'd like to do, and I know that some people have come up with quantum algorithms that show that, in principle, you can compute these things faster. So some examples that maybe people have heard of are Grover's algorithm, Shor's algorithms. These are algorithms that are very large in terms of resources that you need, and I'll talk a little bit about resources in the next couple of slides. And you say, okay, the computers we have today, they are definitely not capable to run these very large algorithms on these large problems that we care about. So what we will do is we will look at understanding, if we had a very powerful quantum computer, what are the things we could do with it for use cases in a provable way that we can prove that we can do things faster than what we have today, and how powerful a quantum computer do we need, right? Once you find that algorithm, you also ideally would like to answer the question, and also this is how powerful a quantum computer we need. So that's kind of a top-down approach where you're solving things from a bigger picture, not necessarily a bigger picture, but I would say from a future standpoint, and say, okay, this is something we could do in the future, and how do we try and bring it as close as possible to now? The bottom-up approach is almost the opposite, where you say, okay, we have computers today that can do things, and as far as we know, we can't solve, or we wouldn't use them, and I'll talk a little bit about that too, to solve real-world problems, but we can maybe solve some example problems on them to study these algorithms in real hardware setting. And that could also give us information. And as the hardware keeps getting better and better, because of the very hard work that very smart quantum hardware scientists put in, we can experiment and try and understand bigger and bigger algorithms in this noisy environment. So that's the kind of the opposite bottom-up approach. So those are 2 ways to try and solve use cases of quantum algorithms. The other 2 buckets are a bit different. So the third bucket, I've written bringing algorithms closer to reality as a whole. So this means that if you can find things like tools, theoretical tools as well, that can help help bring quantum algorithms closer to reality. So one example I've written is error correction. So qubits are very noisy, and there are error correction schemes that are out there in theory to make sure that your calculation at the end is less noisy. But they require a lot more resources. So you can think of it as, for every qubit that you want to use in your calculation, you need, depending on various things, like 1,000 other qubits, let's say, to make sure that you correct the error that could possibly go in that qubit. So if you can reduce that number or find cleverer error correction schemes, that suddenly applies to a whole load of different algorithms and can make them more readily, or bring them closer to being readily usable. Another one is, for example, quantum arithmetic. So in your quantum algorithm, at one point you'll say, well, okay, I need to add these 2 numbers as part of my algorithm, and that takes up, resources in terms of you need to use qubits and gates and things like that. If you can improve the efficiency of those things, then suddenly all your algorithms that require at some point to add 2 numbers, which is like a lot of them, suddenly that makes that algorithm slightly easier. So these are kind of algorithms that, or techniques that pervade many algorithms. And finally, the last part, which is looking at currently viable algorithms, which is using quantum-inspired classical algorithms. So there are some very clever people that are working on this. I am not working on this, but they look at these quantum algorithms that have come out, especially these sort of top-down ones, which say we need this really big quantum computer and we can do these cool things. And they say, well, okay, I can never reproduce exactly that on my classical computer. But there are some ideas from there, some ways of thinking, some techniques that I can take and put into my classical regular algorithm and make an algorithm that's better than the others and that can actually run on real computers today. So those are sort of 4 buckets of which I think about the quantum algorithm space. Today we will talk mostly about the first one. That is because our work at Goldman Sachs tends to be focused on the first one more than the others. Okay, I will take actually I'll wait another few seconds if there are any questions. All right, then I'm moving on to talking about these top-down approaches. Okay, so I've talked a little bit about the rules of the game and how we think about algorithms. And so the rules of the game are the very nitty-gritty, and how we think about algorithms is a bit of a big picture. So let's try and kind of find the in-between. So here are some examples of problem classes that we know quantum computers can solve, right? Quantum computers can solve optimization problems, simulation problems, machine learning problems, cryptography problems, even differential equations in some situations, and some more actually. But we are not necessarily interested in just quantum algorithms that can solve these problems. What we really care about is how do these quantum algorithms compare to their classical counterparts, right? And so we can think of these, or I think of them in 4 ways. Or 3 ways, sorry. One of them is that there are algorithms that maybe perform faster on a quantum computer than a classical computer, but we're not sure yet. So we're still investigating and we're learning. And usually the types of problems that are in here are machine learning and optimization algorithms. They sit in this maybe faster bucket. There are some that we know will perform asymptotically faster, and actually I should add machine learning, because recently there have been special case machine learning algorithms that we know will perform asymptotically faster, some optimization algorithms, simulations, and cryptography. We know that this will perform asymptotically faster. So asymptotically faster, another way of saying it for those that are familiar is this big O notation. It's the idea that if as your problem size grows, you will be able to perform better, right? So you can have the size of the problem, let's say the most famous example of in cryptography is Shor's algorithm. So you're trying to find essentially the prime factors of a large number. As that large number grows, right, the classical algorithm takes exponential amount of time in the number of bits of that number. Whereas the quantum one takes, it's not exactly linear, it's polynomial, but this is just a cartoon to show that if you have some quantum algorithm that can not grow, the time it takes to solve the problem doesn't grow as fast, then now suddenly you've got an interesting situation, right? And so you have some things here which are shown, you have some examples of algorithms that are shown provably to be asymptotically faster. But then what we want to get to is something that is eventually practically faster. So the example here that I put is cryptography. So as you can see, this is a great example, this cartoon, of something that if you think of the linear line as how much time the quantum computer takes to solve a problem, and this exponential time as how much time it takes for a classical computer to solve the problem, you can see that if the problem size is quite small, you would actually definitely use the classical computer because it takes much less time for this problem size. So what's interesting is to find problem sizes that we care about, that are big enough for these asymptotically faster algorithms to be useful. And Shor's algorithm is a great example of this, where indeed, if you want to break, for example, RSA cryptography, you cannot do that ever with a quantum computer. The problem size is very, very big. You need to solve a number that's, you need to find factors of a number that's 2 to the power 2048, let's say. Gidney and Ekara in 2019 took Shor's algorithm and computed how many resources would we need to actually perform this operation. And with 20 million noisy qubits and other resources, which I won't specify because I'm not an expert in this field, but they say we need roughly 8 hours to decrypt an RSA encryption. Whereas, like, if you wanted to use a classical computer, it'll essentially take you like thousands or tens of thousands or millions of years. I don't know, some ridiculous number, right? So that's where we really, this is where, you know, top-down algorithms get really interesting. So the idea is to try and take some of these algorithms that are related to finance and put them in this bucket of eventually practically faster. Try and bring them to a stage where you say, well, okay, we know that they're asymptotically faster, but also in these conditions, we know that they'll be eventually actually practically faster, and we would care about using them in real world situations. And so how do you do that? Very briefly, the way you go about doing this is you do it in 3 long steps. You say, first of all, if I have some algorithm to solve some problem, what is the algorithm and the gates? Like, how do you decompose this algorithm into quantum gates, right? As opposed to just arbitrary functions. Not arbitrary, but like specific functions, but that are not decomposed. Then you say, great, I've found out, you know, what the gates are. And you don't necessarily have to be like, okay, I'm going to draw the whole circuit, but you could say something like, well, okay, to add 2 numbers, if they're this big, you need this many gates and this many qubits. Okay, so I've done that part. Next part, okay, I take the previous qubits that have come out of the first step and see how many new qubits I need to add, or ancilla qubits I need to add, how many gates I need, and so on and so forth. And once you've done that, you count. You count the number of qubits, and you count the number of gates, and specifically, for those of you who are more familiar with the field, you count T-gates, because T-gates are the ones that eventually will be very hard to produce in an error-corrected, fault-tolerant quantum computer. And then finally, once you've got that, you say, okay, well, I have this algorithm, and I know how many qubits I need, and how many T-gates I need, and how many operations, so how many T-gates in parallel I need to perform, right? So, or I should say in series, sorry. So how many times do I need to use T-gates? And if I use 2 T-gates, I count that as like 1 usage. Sorry, 2 T-gates in parallel, I count that as 1 usage. Okay, so I know how much, you know, I know what I need. Now, how much time should it take, right? I say, and that question is answered depending on the use case. So you say, okay, I would like to compute this. In today's world, we compute it, you know, in this much amount of time very happily. So if my quantum computer needs to be useful, it better be able to compute what I want to, which is requires this many qubits and this many gates in at least, and at most this amount of time, and whatever that time is, right? So let me be a bit more specific about what I mean by these gates and qubits, and we can really understand these metrics. Before that, I saw that there were a couple of comments, and I'm happy to take that. I think some of them have been answered. I think...
But no, Rajdeep, I think it would be good if you share your thoughts also. Okay.
So yeah. I think for the quantum walk, I think this is the answer. A couple of people answered and they said, okay, listen, like it's not clear and it could be used in potentially search applications. And that's true. So essentially that's my limited scope of quantum walks as well, that it's really interesting to solve specific math problems faster than you can do on a classical computer. But those math problems tend to be very specific to math and not necessarily have a commercial use case. The idea of whether it can be used to solve math problems that industry or somebody cares about outside of the concept of trying to further our math knowledge is still, I think, unclear. I mean, you could definitely use it to solve certain problems that you would use to solve that whatever problems regular classical random walks can solve, you can solve using a quantum random walk. But the question is, would you use a quantum random walk? Because it would essentially, because of all the overhead, it might take more time. So I think that question is still up in the air. We haven't found a great, I would argue that there's still not, to my knowledge, a smoking gun use case of like, okay, great. As soon as we get a good enough, powerful enough computer, we can use it to do a quantum random walk to solve this problem faster than anything we've done on a classical computer. Regarding quantum machine learning, so the other question is, can you comment on the special case machine learning algorithms that are asymptotically faster? Yes, I can. So I will comment on, there are a couple out there, but I would say the most interesting one, or not more interesting one, but the most recent one is one that came out in, because they're all kind of interesting. The most recent one came out in actually this December, and it was a paper by Robert Wong, who is a grad student at Caltech. So he in collaboration with people at Caltech and at Google, and at a few other institutes actually, came out with this work on using quantum machine learning to understand physics experiments better. So the idea is that if you have a physics experiment and it produces quantum states, right? Your physics experiments is chucking out quantum states, let's say as an ensemble of atoms or some particles in particle physics. You can do, with a regular computer, what you would do is, well, actually you would first measure all these quantum states and you get the answers to your measurements. And then you can do the experiment again, you would measure again, do the experiment again, measure again, and you have a bunch of measurements, and you take all those measurements and you put them in a classical machine learning model. And they tell you something about your experiment, whether it's the state that it produced, whether it's the quantum channel that it went through, things like that. Instead, if you could, instead of producing these states and measuring them immediately, if you could produce many of these states, so you produce, your physics experiment produces some state, you run it again exactly the same, it produces the same state, you do that again and again, and you take those physics states, you transfer them to a quantum computer, and this is the part which is, they definitely explicitly say, like, listen, we kind of, this is the part that needs to be worked on. It's not physically, there's no fundamental laws of physics that prevent you from transferring a quantum state to a quantum computer, but it's a very, very hard engineering problem. But if you can do that, then suddenly you can use quantum machine learning with these quantum states as inputs to gain information about your state in a much, much faster time, exponentially faster time. So you need exponentially fewer like examples of your state to get to your answer that you would like.
So Rajiv, just to clarify, this is what they call quantum data, right? The input states that you give would that be termed quantum data, or are they talking about something else?
Yes, the data is quantum data. That's right.
Right. Yeah. Thanks. And do you have any comments on if you can use quantum machine learning for classical data?
Yeah. So that is an ongoing. That is a very, very ongoing field of research. That's kind of one of the other holy grails of quantum machine learning. If you just get classical data, can you use that and put it into your quantum computer and make something useful? So as of now, the examples that have come up that have been shown to provably be faster. And by the way, I should say a quick note. Proving stuff in quantum machine learning, I mean, already proving stuff for quantum algorithms is tough. But proving stuff in quantum machine learning is slightly a step higher because there are very few proofs in classical machine learning already, right? Forget the quantum aspect. So just machine learning, there are a few proofs. So now if you add a quantum component to it, it's also hard to get proofs. But so the example I'm going to talk about, even though it's very, very contrived, it was a cool example, and it wasn't obvious. So if you have some supervised learning, if you have a learning problem, it's just a supervised learning problem where you want to classify stuff, right? It's a classification problem. If your data comes from a very specific contrived distribution, and for those of you who are familiar, if it's generated by the discrete log problem is the statement. then you can use, then in order to classify that data, a quantum computer, your machine learning algorithm on a quantum computer will perform exponentially faster than a machine learning problem on a classical computer. Now, that is just one example, and it's a very clean example, and the proofs are very nice, but it's not an example you would use in a real world situation, because as far as we know, data doesn't come from discrete log problem distributions. I think those are the two main ones that I've heard of. If there are any other newer ones that I forgot about or I haven't heard of yet, I apologize. But those are the big examples of potential or advantage in quantum machine learning. There are a couple of other examples. So, do you use Qiskit or Keras for use cases in finance? So Keras is a machine learning, like deep learning tool. So the folks in classical computing do use that. In quantum computing, we haven't used Keras so much, and Qiskit we do use. And this is essentially to understand some of these algorithms. Like if we want to kind of make sure, because we think of, I mean, as the slide shows, we think of stuff still in like logical gates, right? So we use Qiskit to make sure that what we're doing and how we're thinking about things actually for very small situations is what we think it is. And then Vishnu asks, isn't it like the ansatz learning shores? It's even more blatant than that. By asking this question, isn't it like the ansatz learning shores, you're implying that there is a variational quantum machine learning model. And this is not even, well, okay, it can be translated to a variational model, but you're not learning Shor's algorithm. You're actually going to use a unitary that implements Shor's algorithm, which then puts the data into a very nice feature space. So, I mean, I think very briefly to think about it, the data is kind of like, you can think of it as like red dots are 1, blue dots are 0, and they're all scrambled everywhere, right? But if you use this unitary to kind of change the way they're separated in feature space, you kind of take all the red dots and put them to one side, and take all the blue dots and put them to one side in this new feature space. And then your machine learning algorithm just has to learn how to find that separating hyperplane. So the first part of turning it into this new feature space, you're not even making your ansatz learn that. That you're giving it to your ansatz. This is why it's quite contrived, right? You know information about the data, and the data comes from a discrete log problem. And then once you're able to do that through a quantum computer, you also just create the separating hyperplane, which is which is not something that's unique to quantum computers, to create the separating hyperplane like very easily, but you need the quantum computer to be able to put the states into this feature space. Okay, so let's talk about, maybe I think those are all the questions actually. So thank you for asking the questions, and thank you for the people that are answering them as well. So I wanted to talk a little bit about, the resources. So, right, so I mentioned before, like, hey, what we care about is we care about these resources required, and I want to spend a bit of a second. So on the left-hand side, you have a classical circuit. You have 3 bits as your input. You have 1, 2, 3, 4, 5, 6, 7, 8 gates, right? But you have a gate depth of 4, because these 2 gates you do in parallel, these 3 gates you do in parallel, these 2 you do in parallel, on this one you do by itself. And so you have 1, 2, 3, 4 kind of steps of operations, right? So similarly, in this quantum version, you have 3 qubits. You have this is actually 1 gate. So when you see these lines, it's like as if, these 2 go into this 1 gate. You can think of these 3 going into this 1 gate, 2, 3 gates, but you have a depth of 2. So when we mean program depth, we mean like how many times do you need to run gates on separate qubits? And so with this in mind, we can kind of paint a bigger picture, right? So let me show you this empty plot, and I'm gonna put stuff in there. But the x-axis is just the number of qubits. So this is, your machine has 1 qubit, it has 10 qubits, it has 100 qubits, 1,000, 10,000, and it's in a log scale. And this y-axis I've labeled as program depth, and it is kind of just how many operations can your computer do before the answer becomes nonsense, because there's so much error that gets injected because it takes time to do the operations, because every operation injects a little bit of error. At what point, what is the depth at which I can say, for some hand wavy way, look, the answers will be fairly reasonable for whatever algorithms I want to solve. Okay, so let's put some stuff on this plot. So this is hardware stuff, and there's a lot on this plot, so let me just go through it with a little bit of time. So this dotted line that you can see here, along with this dotted line, and everything that is light purple, or sorry, almost see-through purple, is where classical computers can simulate things efficiently. So let's take this point over here. So this point is if your program depth is 1 million and your computer is something like 3 qubits, I don't need a quantum computer to do it. I can have a classical computer do it as efficiently as I can, because it'll simulate it in a much faster way because of the overhead required to simulate on a quantum computer, right? And so this line over here will kind of move a little bit to the right over time because classical computers, of course, people are working on those too, but it won't, because again, since this is kind of logarithmic, it's not going to move heaps and bounds, right? Similarly, this line down here, so this is just saying if you have however many qubits you want, but you literally just have one operation that you need to do on them, like one program depth, where the operation is just like 2 or 1 qubit gates, it's fine. You don't need a quantum computer. You can just simulate this on a classical computer. The blue boxes are what we have today in terms of quantum computers. So you can see that most of the quantum computers we have today are within this classical regime. And there are a couple of results that are sticking out just a little bit. So Google's computer in 2019, this is the Sycamore one, showed here. So we have 54, 56 qubits or something with a program depth of a little less than 100, something like 70, I think. But that number I don't remember exactly. And here we have the Hefei lab in China, and then now we have IBM Eagle has a point over here. Sort of, they're still putting out the specs, but this is what it's looking to be like. So this is the hardware. Now, what do we have in terms of algorithms? Well, we have stuff going on here, which is these noisy intermediate scale quantum computers, and we have these big algorithms like Shor's and Grover's. These are the sort of top-down or fault-tolerant, as we call them, algorithms, right? And as you can see, they kind of lie in this gray section where we don't have the hardware yet. So we're getting there. But also these boxes, as you can see, they're very big. Like I haven't put any dots, right? There's actually a Shor's algorithm dot somewhere here. I think it's up here somewhere. But otherwise, there are not many dots that have been put on this plot. I'm sure there are a few others that I haven't mentioned, but I think a lot of the work that we would like to do is put some dots on this picture. And now this is where we get a little bit into maybe the financial use cases. So in 2020, we put out a paper saying, hey, if you want to price a derivative that we care about, that is often priced and that is quite complicated, we need your quantum computer to be here. And I'll talk about the exact numbers in a second. But this is how good your quantum hardware needs to be. And similarly, if you want to do risk analysis, this was in 2021. Very recently that we put the paper on archive and it's still going under peer review, you need a quantum computer that's like this good, right? So this is hard to get to, and it is down the line in the future. And people will ask, well, when can we get to the state of running, close to 10,000 qubits with millions of T-gates? And then I think the answer is definitely not like next year, but maybe the hardware people will know better what the answer to that question is, because I'm not a hardware expert. And so I wanted to talk a little bit about that. So with that context, actually, I wanted to talk, let me just check that that's what I'm doing. Yeah, so I want to talk a little bit about the work in finance and things that you can think about. Actually, yeah, I might as well do that because I only have a few slides left. So this is an example of stuff that we've done in quantum computing at Goldman Sachs. So I wasn't a part of all of this work, but I was a part of some of them. But essentially, they all rely around trying to understand what it takes to make quantum computers useful for derivative pricing and risk analysis. So what that means is that at the firm, we sell and buy a lot of options, autocallables, financial assets, right? And so first of all, we have to price them. And in order to do that, essentially you run simulations. And you use Monte Carlo methods. And then also we would like to not only price them, but after we sell or buy them, we need to hedge them. And so in order to hedge our assets, we need to calculate the risk on our assets so that we can, as much as possible, hedge them. And so that requires also a Monte Carlo simulation plus some derivatives like gradients, like calculating first derivatives in the mathematical sense. And so all this work here is kind of looking to understand that. And that comes in the kind of simulation category. And actually, maybe I should quickly go back to that slide here. So that derivative pricing and risk analysis comes into the simulation category. Oh, did it stop sharing? Might have stopped sharing. Why did it do that? Can you guys still see it or no? It's gone.
No, we don't.
No.
Okay. Yeah. You go to. There we go. Okay. Okay, so in this simulation is where the bucket of derivative pricing essentially falls, and then in a few other examples that we're thinking about, but we haven't, we're still working on it. One is in the optimization bucket, so you can use optimization to basically optimize your portfolios, right? That's a big thing in finance as well. So we have our assets and we want to understand how to maybe minimize the risk in a bigger picture so that all our assets are like stable, and in case there's volatility, we don't experience as big a shock. And in machine learning, you can think of the usual. I mean, again, what I'm saying is not so revolutionary, I feel, but the uses of machine learning in finance are that of in anti-money laundering, in credit card fraud, in even stuff like recommendation systems. So we have some clients where we understand them very well and we'd like to recommend assets for them to buy depending on the data that we receive. And so really, like, I think the answer is to where can we use quantum computers in finance is, well, anything that you want to use regular computers for in finance, you can try and think of ways that you can use them, that you can use quantum computers to solve similar problems. And right now, like as I mentioned, we've done some work on the simulation aspect, which involves derivative pricing and risk calculation. And then optimization, we're starting with trying to learn portfolio optimization, and then machine learning as well. We're thinking about potential use cases down the line. So, so I wanted to actually flash this slide, which was kind of maybe the second slide that I mentioned of the main takeaway. So this kind of goes back to asking the question, right? Like, how, like, when can we find quantum advantage in finance? And so there are two specific examples that we worked on to give you a concrete number. So in derivative pricing, so if you have complicated options essentially that you want to price, you need a computer with 10,000 qubits, logical qubits. It needs to be able to perform a program depth of 10 million roughly. And it needs to be able to do all this in 1 second, because otherwise we would rather just use what we have today. Similar for risk analysis. So if you're trying to calculate Greeks, any first order Greeks, for those of you who are familiar with finance, but this just means basically if you're trying to calculate the derivative of the price with respect to the derivative of the price of your option with respect to either the price of the underlying, with respect to time, with respect to volatility, you need roughly 6,000 logical qubits, a program depth of 1 million, and this all better happen in roughly 10 seconds. Otherwise, again, we would just use what we have today. So why, maybe to sort of finish off the technical bit, I can answer the question, well, why do we work so hard to come up with these numbers, right? And then put it out there. So the two main reasons is, one, from the hardware side, it gives the hardware community a benchmark to determine when we can achieve quantum advantage. So now, instead of just, I mean, it gives them an extra point of like, oh, hey, like if we're building towards this use case, we know where we're at, right? We know where we stand and we know how much time, or not time, sorry, we know what we have to do, what are the things we have to solve to get to that point. And on the flip side, it also informs the quantum algorithms community that we are hoping to get people interested in these types of algorithms and work on improving the resources required. So reducing, ideally, the number of logical qubits in the program depth, such that it can get closer to being useful one day. So it's kind of like the hardware people are trying to make these numbers higher, like increase their number of logical qubits and their program depth, and decrease the time that they can perform all these things in. Where the algorithm side are trying to find algorithms that require less of, like fewer qubits and fewer program depth, and whose classical side needs a lot of time. So this kind of adds to this puzzle of trying to bring these two together. Okay, I think that's what I'll stop here, and I do have a bunch of slides about this first paper on derivative pricing that goes into a little bit more details about how we think about the algorithm and how we compute the number of qubits required and things like that. But before that, I wanted to end the main part of the talk with this slide. So this is a little bit different to the rest of what I've talked about, but it's essentially that in quantum technologies, like in most tech fields, we have our diversity of people is not fantastic, but there are people that care about improving the diversity and inclusion of our community, and there are some really good people from very different communities and representations that are very, very good in the field. So I've just flashed up a couple of images of people that they look different, obviously, and they come from different backgrounds, and they are very different, but they all have one thing in common, is that they're very, very, or they were very, very technically apt in the field of quantum science at a very, very high level. And so I'm very, although it is an issue that diversity and inclusion and equity is an issue that needs to be worked on in the quantum tech field, I'm very optimistic, and I think because of some very, very good people, we can continue to make quantum technologies a much more inclusive place. Okay, I think I will end on that and put up this slide as kind of the takeaway message. And I am happy to take any questions that people may have.
Hello, Raju.
Hi, Vishnu.
So I was wondering, maybe we could go the derivative pricing on a very high level, just go over the details of that.
So let me go at a high level, and then maybe I can try and let's see. Okay. So I think maybe I'll talk a little bit about a few things. So I'll put up a couple of slides and talk about those slides. And then if we need to go deeper, I can go into more slides. So let's put this up. Let's do this, and let's present. Sorry, I'm looking away because I have two screens. So if you see me keep looking away, it's just because I'm also trying to read the questions and things like that. Okay. Okay, so let's talk about Monte Carlo for options or derivatives pricing. So in derivatives pricing, what we do is we run a bunch of simulations, and then we take the average of all those simulations, and we essentially say that the price of our option is the average of those simulations, right? This is a very quick way of saying it, but I think that's essentially, I mean, I don't think it's conceptually much more crazy than that. Of course, the devil's in the detail. But in doing this, so this is called the Monte Carlo simulation, and it requires, and in principle, on a quantum computer, you can have a quadratic speedup. So that's what you see down here, right? So you say, okay, if you were running n simulations by which you're using n times some function to run the simulation. On a quantum computer, you need to use just square root of n times that same function, or that not exactly same function, but the analogous function on a quantum computer. Because remember, classical computers and quantum computers at the very fundamental level work differently, but you can kind of implement a similar function in both that look a bit different, but that serve the same purpose, let's say. But all that to say, you need to run it fewer times. But now the question is, okay, that's great if you need to run 1 trillion simulations, or I don't know, 10 to the 20 simulations. For sure, just let's use the quantum computer, we're ready to go. But, or at least, you know, if you can, we can definitely do it faster on a quantum computer. But when pricing derivatives, we generally don't tend to use more than 1 million simulations. And sometimes it's less. So that's why the question of like, okay, can we use this to price derivatives and how useful is it comes up. So I think let's talk about just financial derivatives maybe for people who are not so familiar. So in finance, derivatives are assets that pay depending on a function of some underlying asset. So the most simple example in a real world case is called a call option. So a call option, before going through these like numbers, is saying, hey, look, I want to buy some stock in the next 3 months at this many dollars. And I want to have the option of buying some stock in 3 months at like $10, let's say, stock X. And then, so of course, if in 3 months stock X is worth $20, well, that's great. You made a bunch of money because you buy the stock at $10 and you sell it for $20 and you made $10, right? So, and if the stock is in 3 months, if it's like $5, then you say, okay, I'm not going to buy this stock at $10 because I'll just lose money, so I won't exercise my option, right? And so this is just, all this stuff is just a formal way of describing that. So you say the price of the stock today is some S0. The strike price, sorry, there's an I missing, for which you agree to buy the stock at is K. So it's like, this is the one where it's like, hey, in 10 months, I'm gonna buy some stock at K dollars. The payment time, so T is like, well, I said 3 months before, and then 10 months, it could be any period. And then the payoff. The payoff says, okay, well, for a call option, it just says whatever the price is in T time, let's say in 10 months, I'm gonna subtract my strike price from it, and I make that much money if the price that I agreed to buy it on is less than the price of the stock at time T. Or if it's more, then I just don't buy it and I made $0, right? So if we knew what S of T was going to be, what the price of the stock after 10 months is going to be, we're like, great, we could just price this option. We could tell you how much we will sell you this option for. The option of you to buy the stock wouldn't be very useful because the other person would know too, and why would they choose an option? They'll just wait. So what we do is we say, well, okay, if we don't know it, we need to simulate it using Monte Carlo. And this I'll go very briefly, but we simulate different possibilities of the underlying stock, of the stock, let's say in the call example that you want to buy. And we use typically Brownian motion as a simulation. and variants of this. This is known as the Black-Scholes equation. And you get some, so this is just saying, well, okay, my return of the stock follows some normal distribution, some random walk, right? And your mu and your sigma are the drift and volatility of the stock, which you can estimate through typically like historical data. And then you simulate a bunch of the stock and you find out, okay, for each path that the stock took, what price should I, if the stock takes this path, what price should I charge the option? What price should I sell the option for? If the stock took this path, what price should I sell the option for? If the stock took this path, and you keep doing it for all paths, and you take the average of all those prices. And that's how you price an option. Now, specifically for the call option, you don't even need to do the simulation because you only care about the final price. And therefore, it turns out you can actually solve this equation analytically. If you say, I want the expected value of this function here, given that my prices follow geometric Brownian motion. However, most stocks are more complicated. One, because they will, more options, not stocks, more options are complicated because they will have, first of all, they might have several stocks, right, underlying that option. It might not just be an option to buy one stock, but several stocks. Also, by the way, I use stock options as an example, but this can be in currency, this can be in commodities, this could be like whatever you want, whatever financial thing you want to buy. And secondly, the price, the kind of deal that you make may not only depend on just the last price, right? You could say things like, okay, well, it'll depend on the last price, but also if the price ever goes below some amount, I want the whole contract to be voided. Or if the price ever goes above some amount, I want to gain more. You know, you can make whatever path-dependent criteria you want to. And so now it gets complicated to solve analytically, and actually most of the time it's just impossible. But what you do is you do the same thing. You run simulations and you get the average. You get the price at every path, and then you compute the average. Now, what you can do is, instead of doing it classically, you want to do it in a quantum way, right? So how does that work? In one sentence, you use amplitude estimation. So actually, let's see if I can find the papers that were relevant for this. Yeah, so, well, I'll put them up as well, but there is amplitude estimation is actually given in this paper by Brassard et al. And then how to use it to solve Monte Carlo problems was given by Montanaro in 2015. And essentially, what you do is these steps over here. So formally, you're trying to, I said you have a bunch of paths and you want to find the average, and the average is the expectation value formally, and so this is the integral. So all this kind of funky notation is saying is, okay, this is some path, and this is, S is some path, so it's just one of those lines. F of S is the amount of money that I will make if that stock happens to follow that path, and P of S is the probability that it followed that path, right? So you just keep multiplying the probability by that path and you add them all together, and that's your average. And so the idea is that if you do it in a classical way, the number of paths you need is 1 over epsilon squared, where epsilon is the error with which you're okay with. Whereas in the quantum way, you just need 1 over epsilon. So how does that work? And again, I'll keep it fairly conceptual just to make sure we finish in time. You actually go through all the paths at the same time, because you could put everything in superposition, right? And this is true. In a quantum computer, you can run multiple possibilities at the same time. And in addition to that, for every single path, in one shot, you can compute the payoff as well. You can say, okay, for this path, this is how much money I'll make. For this path, this is how much money I'll make. This path is how much money I'll make or lose. And then you can, and then you have your answer, because it's just a sum of all the amplitudes in the superposition state. You have your answer sitting in quantum superposition. And this is done in one shot. There's no like O(n) squared, no nothing. But on the other hand, if you make a measurement now, you will collapse the state into just one of these paths, and you'll get the payoff for just one of those paths. And that defeats the purpose, because one way you can do this is you could just keep doing this again and again. So you load all the paths at the same time, you make a measurement, you get one of the payoffs. And you do it again many, many times, then you add those and you divide by the number of times you measured. Now, that is the same thing as simulating every path on its own. Another way you can do this is to extract that information using something called amplitude estimation. So this is an algorithm that says if you have some quantum state, and let's take the easy example of alpha 0 plus beta 1, and you want to estimate beta, I can do this for you without just measuring, and it's quadratically faster. So that sentence that I said was very terse. There's a lot going on in that sentence, and none of it is obvious. But in using amplitude estimation, you can extract this value. And that's actually, within amplitude estimation, is where you need to reuse this f of s function many, many times. And actually, you need to use it square root of the number of times you would have used it classically to get the same error. So essentially, you perform amplitude estimation as the workhorse. So you take, let's see. Sorry, there's a lot going on here, but you take your answer. So you take your answer that you're looking for, right, which you do in one shot. You put it as the amplitude of a qubit, and then having done that, you can extract that amplitude using amplitude estimation. So if you look at the state, which again is lots of stuff going on, but the state just tells you for this path that the asset took, it has this probability of happening and it has this payoff. And so you sum, and you're in a superposition of all paths. So it turns out that if you estimate the amplitude of this one qubit, and if you do the kind of multiplications, you will actually be estimating this value over here, which is the square root of your expected value, which is what you want. So I think I'll leave it at that for the explanation of what we did, of what it is. What we did is we took specific examples, we mapped out some parts that were, so quantum, like Monte Carlo using amplitude estimation was already there when we started this project, and we definitely used a lot of it. But we mapped out a little bit of the previous steps of loading this distribution, because I say, hey, you simulate all the paths, right? So that part was a little bit non-trivial. And so we worked on that part, which was sort of the addition in terms of quantum algorithms. And then we said, okay, now that we have that first part and the second part and everything together, let's just see how many resources we need. And that's where we ended back up in this slide over here. So where we came up with these numbers. And the 1 second, where we said we need to do this in 1 second, is because so the way we work generally is we talk with the business and ask them, hey, what problems are interesting to you? What problems would help if you could do things faster? And then in this specific problem that we came up with, another question we asked was, okay, great, this is a really interesting problem. We think we can do something useful with this. How long does it take you today to solve this problem? And they said 1 second, without elaborating on exactly what techniques they use, but they are Monte Carlo techniques. They say we can solve it with our computers in 1 second. So that was what I have for the Monte Carlo part for now.
Thank you.
Thank you for the question.
Participants, please feel free to switch on your mics and ask questions, or drop them in the chat. Yeah, I think we have reached a good position. Maybe, and we are also reaching time too. So maybe let's wrap up. Vishnu, if you want to take over.
Yeah. So with this, we come to the end of the session, and I would like to express my sincere gratitude to Dr. Krishna Kumar for taking the time to enlighten us about the applications of quantum computing, especially in the field of finance. I would also like to thank our coordinators, Dr. Lincy and Vishnu Ajith, without whom this event would never have happened. Last but not the least, I thank every one of you for attending this webinar, and I hope all of you have found the session to be captivating and helpful. With this, we close today's session. Thank you all.
Thank you.
Thank you all for joining.